question. You mean that you're talking about particle interaction and symmetry? Do you agree? Is that your question? Why my question is, why did you mention the symmetry? How much do you know about the symmetry in the context of particle physics?
Not much.
Where did you get this idea from? Textbook? Can you show me?
It's from
Okay, you can. Yeah. Because it's very abstract idea. This idea has been successfully adopted in a developing standard model, right? But I don't think it's necessary for students to learn this. But so that's why I would like to have look of this particular part in your textbook. Yeah. This is this Feynman diagram, right? Space time.
I also have this other revision book that talks about symmetry.
Yeah, symmetry is very important. So basically, they say you have to consider that there's time reversal, right? So if you look at this diagram, and the direction of the antiparticle move is opposite to the particle. Can you see that? So that is one example demonstrates that there is a symmetry about the time. Can you see? So this symmetry, if you want to know more, is that you have to. So basically, if you have the particle, then they should have antiparticle. That is also called symmetry. Right. So depending how much do you know about this idea. So in this first paragraph, and they are talking about the law of phase do not under certain transformation. Yes. So that is if they for example, if you change the time direction, right? And the optics, you see, we have seen this symmetry in the when we study optics. I just draw the diagram, not necessarily in particle physics. In physics, there's symmetry here. I can't participate. Anyway,
I'll stop the screen sharing for the whiteboard.
Okay. So basically, a good example to understand this symmetry issue in physics, let's go to whiteboard, is a study of the optics, right? So if you remember, in a geometry optics, we put a lens here. So we put a lens here, and put an object here, right? For example, we put this is candle here. This is candle, right? The candle is bright. So what we can do following that Snell's law, not Snell's law, this is called lens maker's law. That distance is focal length, right? And so that will give, this is from the center to the, this is a good example to demonstrate the symmetry issue. So if I draw a light ray, can you see if you draw light ray, go that direction, and then and then continues according to this optics, according to the lens maker's law, and this will go that direction, will change the direction, right? And another way is that you can draw additional light ray. This time, they start from candle through the center of lens, can you see? And moving in the direction, a straight line, right? So in this case, you can say the direction of the light is go that direction, can you see? Okay, sorry, other way around. Okay, then we got image, can you see? We got image over here, the image of the upside down. So that is the image of this candle, all right? So this is, can you see? this is object. See, this object, and this is image. Okay. So when we the formula, but if you look at the formula, do you remember this formula? Have you seen this formula? So that is the formula governing these two distance from the object to the image. So that 1 over f is equal to the distance of the object and plus distance to the image. Have you seen this formula before?
No.
Oh, this is optics. Have you studied optics? Not yet?
No, I don't think we study optics.
Yeah, probably we're not studying because you're year 12 now, right? Probably we're not going to study optics. Anyway, I took this example is that if you change the direction of the ray, the formula is still the same. Can you see? If, in other words, in this case, if you this is called the lens maker's law. The formula is lens maker's formula. All right, or you can consider it a law. In this case, it doesn't matter which is what you can exchange these two terms. Okay, the formula is still the same. Can you see that? So in this case, this implies that in this particular optics formula, you don't have to follow the same, they are symmetric, can you see? This formula is symmetric about the image and object. So this is just one example how symmetry law is used, all right? Another thing is, because if you, sometimes you can, then you perhaps use more example. This is return to your textbook. We're not going too far, right? Because this is fundamental issues in physics. We in a high school level, we only talk about very little bit. Okay. Can we return to that textbook? Have you read that part by yourself?
Yeah, I also have another one.
Yeah, why don't you point to your particular part? We can discuss that question. So, which paragraph are you concerned about this idea?
It's not in this textbook, but I have a study book that I got.
Yeah, that's other book, right? Yeah.
And
so symmetry is idea behind this because symmetry is a feature of physical law. Can we say that? And sometimes you will find that we found symmetry from a given physical law, but in other cases we use symmetry to predict whether a formula in physics is correct or not, based on whether we can use a symmetry idea. All right. So now in this case, probably that is talking about they are talking about the charge reverse, time inverse. Yes, that's right. Crossing symmetry. So in this case, I think I realize now. In this case, we should be focused on our discussing in the Feynman diagram. All right. Because in the Feynman grammar, when you draw the Feynman diagram, certain symmetry you have to take into account. Okay. Such as, can you look at the first example in this book? So what is the charge reversal? So if you have reaction, if you change the charge sign, can you see the second equation, mu1 negative, you change all sign of the charge. And you will find that this equation or this this particle interaction still hold, still annulled. Can you see?
Yeah.
So basically you can see the first one is original, which is mu1. Is mu1 positive, become positron and a neutrino and anti-neutrino. Can you see? Now, if you change that, so basically you have to swap the positive to negative, you see? And in the meantime, you have to change the matter to antimatter. Can you see? I think you will learn this symmetry from each particular Feynman diagram. Can you move to next one? What happened to the next one? They got a proton, neutron, right? A plus B plus C plus D. So what is this? This is called a crossing symmetry. This is a possible interaction. There are many. So this again, I think you only learn some idea of just strictly related to the Feynman diagram. Okay. Time reversal. Do you understand what is time reversal? Reaction took the same if the flow of time is reversed. Products became reactant, and reactant became product. So in this case, it's quite different from chemical, right? From chemical reaction. Because in chemical reaction, although the chemical reaction can move to both directions, but it is a temperature driven, right? Or concentration and temperature driven. In this case, according to this Feynman diagram, you can simply use the symmetry, the time reversal symmetry. Can you see?
Yeah.
You don't have to consider whether temperature or concentration is allowed. Okay. And besides, this time reversal is just a particle, the element. This is not necessarily a particle. It is a subatomic particle. Okay. So basically, you see A and B are reversed in time to each other. How do we know? Because in this case, what is the time axis? Can you tell me? In the middle, A and B Feynman diagram. Is vertical is time or the horizontal is time?
Horizontal is time.
Horizontal is time, yes. So that you reverse the time. Did you reverse time? And well, that's slightly different, right? This example seems a little bit abstract because they're talking about the proton became neutron, which is beta decay. It's a positron decay, right? One is a beta negative decay, another is a neutron bigger proton. So neutron goes that way, electron goes that way. Yeah. Well, I think that you just get familiar with this a few examples, but not too far, all right? Because in the absence of any guideline, and physicists can only follow in this hypothesis that if this three symmetry is satisfied, okay, these are three types of reversal, right? Including crossing. So in this case, we should allow, we should permit, we should believe this action could happen. It's kind of you have the guideline, all right, or criteria. The symmetry is kind of the criterion or selection, or alternative. You can say it's called a selection law, right? So, for example, when you because when they have this, when we do this experiment, they use high energy colliders, right? Accelerator. They use a high energy beam, the proton beam, collide at higher energy. So you can imagine that there are hundreds, if not thousands, particles could be generated. All right. Now, without any guideline, it is very difficult to predict what particle has been observed. All right. So that's why they developed this idea that they say, well, as long as as long as the symmetry law is satisfied, then we should predict. Once we know one reaction, we should, by using the one of these three reversal, to predict another type of reaction could also happen. Can you follow me?
Yeah.
So it's just the game, all right? The game is guideline for the game, all right? If you go somewhere to play the new game and you don't know how to play, and they will give you a piece of instruction or guideline, all right? You say, do that and do that, and select that, do not select that. So these very similar activities.
Yeah.
These 3 examples, you don't go too far, okay? You just focus on these 3 examples, which may or may not be asked during the exam, all right? Because there are so many, at the end of the external exam, there are so many such topics, but the examination time is limited, all right? So you don't have to go too far. Just for this particular idea, namely the symmetry, then you just focus on these 3 type of reversal, that's all right?
Yeah.
Because you see, even for the physicists, sometimes they have no way to conduct their research without any guideline, okay? So these, by the way, this is just the extension of the conservation law, such as mass, charge, and other in chemistry. Do you remember? In chemistry, we don't have to consider the, maybe sometimes you have to consider time reversal, but in many cases, we just simply using the mass and the charge conservation. That's enough, all right? So yeah. This idea is just additional conservation law. You can just understand that way, all right? Or you use 2 textbooks to study this topic, right?
Yeah, this is a revision book.
Revision book, yeah. Maybe you can select some problem involve this reversal, you see? Can we look at example first before we go?
It doesn't have any
well, if they didn't give any example, then just focus on this table, all right? When you encounter a problem solving, you just go back to this table to see which is which might be the case, time reversal or the charge reversal, you see. Well, a charge reversal and time reversal are relatively easy to understand because you can change the direction of time. But the crossing symmetry is a combination, right? If they both they occur at the same time or they change, what does it mean, the cross symmetry? Can you read this code?
For any interaction that can occur, any particle can be replaced by its antiparticle on the other side of the interaction still occur.
Ah, yes. You just change the particle to its. Do we change all of these? Do we change any particle or all of them? Doesn't matter, right? You can change one. You can change one, or you can. Oh, this is just like. Oh, I see. This is just like algebra. Can you see? If you put the C on as reactant, then you have put the bar at the top. Can you see that? That's probably easier way to remember. For example, in a nuclear decay, if you want to put a neutrino on the right-hand side, you see? Can we return to the first example, the muon? If the muon encounter the neutrino, could that reaction happen based on the crossing symmetry? Could that happen? Do you know what I mean? Can we go to a whiteboard?
You can write on this, I think.
I think I go, okay, I can write, yeah. Oh, yes, I can write this one. That's interesting. You have too many devices. For example, from this one, we can argue that if you put a neutrino, this this muon, sorry, is muon. Can you see? This muon plus. What I can do, I put this this muon. Can you see? Can we just put the muon here? Let's just take the example to demonstrate. I just put the muon. This is the muon, so this muon neutrino, right? On this side, then I use antiparticle. Do you think this could happen? Do you think this reaction or collision would occur?
Yes.
Yes, right? Oh, they should now be careful. I can't read that. They must have two types of the neutrino. What is subscript? It's too small. Oh, yes. One, oh, that's one is electric type. Yes. One is electric type. That's muon type. Yes. So what I did, I just put this muon electric type to this side, to this to the reactant. Can you see? So that should be still happen, right? That's right. Yeah. That's right. Yeah. So this need to get a little bit abstract. Doesn't matter. We can always return to this table if you have the problem solving. And besides, each textbook requirement from each textbook are different, right? Sometimes it is required in one textbook, but is not required in another textbook.
Yeah, I think it's in the syllabus, which is why this revision book has it.
Yes, yes, that's right. Yeah. I think the particle and the relativity or standard model and the relativity are minors compared with you know, the project motion, the induction, this kind of thing, right?
Yeah, induction.
Yeah, electromagnetic Faraday law.
Oh yeah.
Yes. Because you can't do much about the standard model, all right? Apart from this detailed description, you have to memorize. Also, you have to memorize this. Can you see? I don't. In Australia, I don't think they ask students to memorize things. They probably will just ask you some basic question. Just a few, probably 2 or 3 questions about standard model and relativity. All right.
On the topic of electromagnetic induction.
Yes.
I had a question about transformers and how they
work. Yes, that's more. Yes, that question can be more frequently encountered. Yes, transformer. Yeah, can you go to your transformer? Can you go to your textbook to your transformer? Yeah, so they are basically a transformer is an application of the electromagnetic induction, in which the power can move in the field. Can you see? The energy can be induced, or voltage rather. A current and voltage can be induced without actually using a wire conductor. So that is something interesting. Induction, yes. That's right. So this diagram shows that so this transformer had contained this called the primary. So the pair of coil. Can you see? This is called the primary. This is called a secondary. Or in the primary, we got the source whose current or voltage needed to be changed on the other side of the transformer. Okay. Now, how can we do that? Well, we can build 2 coils with different turn, with different number of turns. That in that way, we should be able to achieve our objective. Do you know why? Do you know why? Can we go to the whiteboard to discuss the transformer? Yeah. That is, yeah, I think that is more important than the Feynman diagram. So if you just use this diagram here, this is optics, this is a transformer. Transformer is very useful in industry, and that can be used to change the voltage or current. Can you see? If I just redraw that diagram, this is a cross section of that core, this metal core. It could be an iron core here. Can you see? This is iron core here. So this is the iron core, iron core. It's just metal, okay? And you got a pair of the wire here, a coil here. One is here, I just draw a few. Okay, you can draw many turns. So this is one of them. So this is one pair of them. So important thing to understand is the number of turns. Can you see? So basically, this is primary. This is primary side. Primary. This is like a input. Okay. This side is secondary. Secondary. And similarly, we can build the coil. So this time we have to make sure we are use we make sure when going this winding, we have to make sure we are use the same. We are doing it in the same direction. Can you see? You can hardly see that. I just show you later. So basically, I just draw a few coil turn, but you can this number of turn can be as many as designed required. Can you see? Can you call the n sub p? Can you see? And it is n sub second. Okay. So n, what is n? N is the number of turn. You see, of turn in the coil of turn. For a coil, for the coil. Okay. Now, if we just if you want to know the principle, we have spent some time to understand. But by the way, before that, I just probably give you the formula. We prove that. All right. This is probably the easier way to learn this part. So if you apply the voltage here, the cross voltage, this is a V primary. Okay. Then you would expect the voltage will change to secondary. Okay. And there is a simple relation formula for that. That is voltage primary over voltage secondary is simply equal to the number primary and number, sorry. All right, so this is result. This is summary, can you see? This first formula you need to know when you use transformer. Okay.
Yeah.
Another question is what would happen to the current? Can you see? If this current I is primary, of course, this is not DC current. By the way, these are all the AC current. All right. That's the AC current. You cannot use transformer for DC voltage or current, okay? Because this, I will tell you why. They must be time dependent, okay? Time dependent. Now, given this formula, what can we do with for relation between current primary and current secondary? How do we know? Given this one, how do we know that? So I will show you how to obtain the second formula first, all right? So assumption we made is that, so how do we prove this formula? We have to assumption, okay? To prove, to derive this formula, just as we just assuming, this is how to solve this question in history. Assuming the power doesn't change, can you see? P primary is equal to the P secondary. Or in other words, no leakage, you see, no leakage or no energy disappear, okay? No leakage. Because if the magnetic field, in other words, if I draw the magnetic field, so what does it mean? That can you draw the magnetic field? Can you see, because of the coil, the field can or prefer to go through this metal coil to form a loop. Can you see that? So this is a magnetic field. Of course, they change direction periodically. Can you see?
Yeah.
But that is how you draw the magnetic field in the transformer. Can you see that? In other words, all the loop are actually within that metal core, ion core, right? So that is that is assumption. That's first assumption. There's no leakage. Another thing is that no energy lost. Okay, no energy lost. So, for example, but for the real transformers, this is called ideal. So these two conditions is called ideal transformer, ideal model. Okay, ideal transformer. But for the real one, these two conditions cannot be satisfied. No energy lost. All right. You can't, because the coil got the resistance, right? Any resistance, when you apply the current, they regenerate heat, right? So that is why, unless you use a superconductor, all right? Unless you use, so this equivalent to just or using the Y is a superconductor assumption. So if the conductor is a superconductor, you see, it's superconductor. So which can without the loss, okay, that's called transformer right here. This is a transformer. So this ideal transformer condition, okay. So that if that's so, we can use this power equation. Can you see? Okay, what is a power? What is a power in terms of current and voltage? Do you remember? Power, electrical power. P, what is a P? Do you know this formula, product of current and voltage? Do you know this formula?
I thought that was Ohm's law, resistance equals current times voltage.
No, this is not voltage, no. This is definition of the power. You want to have a look? Can you see? I took this corner to prove that what's the power. Power is energy. This is changing energy, okay, over time. Delta T, that's called that power. Can you see? Okay. In the meantime, the change of energy also equal to energy work done. Can you see? Divided by delta T. Can you see? And work done is equal to F multiply delta X. Can you see? To move the charge to the cross X, delta T. But what is F? F is equal to charge, okay? Charge multiply the electrical field. Can you see? Yeah, this little bit of formulation here. Divided by delta T. Can you see? Or you can use delta Q, it's easier. Okay. So that is the formula for the power. Can you see? The first formula is a definition. This is original definition, all right? Yeah. And this form, in the context of electricity, we can further rewrite this as, if you can follow me that. So what is the delta Q over delta T? Can you what's delta Q delta T? And also current, do you say current? Yes. What is E multiplied delta X?
I'm not sure.
Then you have used, can we use this idea? So if you have parallel plate here, right? And if the voltage between the two parallel is V, the voltage, can you just draw this diagram? The voltage connect with the battery, can you see? If the voltage is V, and this distance called delta X, all right? Yeah. And then the uniform magnetic field here will be, can we use this arrow to indicate the electrical field? So this red color represents the electrical field E, all right? There is a simple relation that the voltage, or sorry, the electrical field is simply equal to the voltage divided by delta X. Can you see that? So therefore, this term is voltage. Got it? So that is how we derive the formula for power in electricity. When you study electricity, when you study the mechanical motion, you use this formula. When you study when you study Newton's law, you use this formula. Can you see? So work is this work. Can you see? You can use this formula when you study Newton. When you study the motion, okay, mechanical motion. But when you study electricity, we will use this formula. We'll use this formula. This one. Can you see that?
Yeah.
Which is the formula written down here, all right? So if we use this formula to assume that no power loss, okay? So the input power will equal to output power, or primary power will equal to secondary power, right? So that will allow us to write this formula here. Therefore, can we rewrite the P as a product as current primary, voltage primary should equal to current secondary multiply voltage secondary. Can you follow me? So if we combine these several equations, so what do we have now? In the first place, we know that the primary voltage divided by secondary voltage is proportional to his number of turns. Can you see? Is direction proportional? Is our first equation. Second equation is that current P primary multiply primary voltage is equal to current secondary multiply voltage secondary. This is our second equation. Can you see? We just derive this formula by assuming there's no energy loss, no leakage of the magnetic field, right? So what can we do from equation 2? Can we rewrite equation 2? From equation 2, we can rewrite IP over IS. Can you see?
Yeah.
That will be equal to VS over VP. Can you see? Well, this is our third equation. So then we do substitution. If we substitute equation 1 into equation 3, what can we obtain? Can you write it down? That is how to derive the second equation for the transformer. In terms of number of turns, yes, can you see?
Yeah.
That is a second important basic function formula in transformer. So in many cases, you just apply this. You can apply this formula. Can you see? One moment. You can apply this formula for transformer. Can you see? Slightly different, but it's relevant. Can you see that?
Yeah.
Now, we haven't proved this first formula. How can we prove the first formula? Do you want to know? Or not? Or you want to know, we can show. If you don't, we can stop here. So if you want to know, I can just draw this diagram for you, how to prove the first formula. First of all, this is, just remind you, this is a cross-section, can you see? This is just a cross-section. Let's just draw the inner one. So this one, can we just redraw this one? Can we just redraw this as a single bar, this single cylinder? Can you see? You have used your imagination. Can you see? So imagine we just cut here. Can we? We cut here. Okay. So this is A. This is B. Can you see? So this part become A. This part became B. Can you realize that? We just cut it and put it to a straight. Can you see? When first cut and put into this cylinder. Okay.
Yeah.
Now we can draw this a coil here. So this is this is a primary coil, can you see?
Mm-hmm.
So in primary coil, you can follow this direction. The primary coil will be here. So primary coil will, maybe I use a different drawing here. I think to make this consistent, I will put this is front. This is front. So that will be the, we can see this part. We can see the part. So this is cylinder. This is the back part. You can see. So then you can easily draw the first coil, the primary coil. Can you see?
Mm-hmm.
The primary coil will go up like this. Can you see?
Mm-hmm.
1, 2, 3. I just draw 3. You can draw many. All right. So we know the turn of here. This turn is in primary. Can you see?
Mm-hmm.
And how about another side? So basically, we got this secondary here, secondary coil in here. I'll draw more if necessary. Okay. So in this case, we can continue to draw this one. So make sure it's this secondary. I can draw the secondary here.
Mm-hmm.
Can you follow me? I just this you can call this transformation, right? I changed the shape, but we just redraw this transformer into this form. Actually, you still can use these devices as transformer, okay?
Mm-hmm.
But unfortunately, if you don't make a loop, then there's some leakage of the magnetic field. Can you see?
Mm-hmm.
So can we just imagine if we have if they got the if the magnetic field in this direction? Can you see? This is inside. This is magnetic field in this direction. Can you see?
Mm-hmm.
And this area, this crossing area, can you see? This crossing area is can we call it A? Can you see?
Mm-hmm.
This crossing area is A. So the blue color represents the magnetic field, and and this is let's write down. So this is A. This cross section area is called cross section. The cross section area, which is in this case is perpendicular to the field. Do you agree?
Yeah.
This magnetic field here. Now, if I ask you to work out this term of the secondary, if you want, can we just write the two flux? Can you see? So that's magnetic flux, magnetic flux. For the primary, so this is a primary. This is a prime. I'm making a table. Is primary. Primary is secondary. Oops, something wrong. This is secondary. So can we work out the flux for both coil? One is primary, another is the secondary. Can you, by definition, how do we work out this flux, magnetic flux? Do you know the definition of flux?
Yeah. Delta B over AB cos theta?
No, that is Faraday's law. Faraday's law is different from definition. First step is to work out the flux. You are talking about Faraday's law, not the flux.
Mm-hmm.
By definition, the flux is just the product, can you see?
Mm-hmm.
Just the B multiply the crossing area, can you see?
Yeah.
And in this case, we have put the number here because each number will double or increase that flux, can you see?
Mm-hmm.
So this is the formula for the flux, can you see?
Yeah.
B is magnetic field, A is a crossing area, which is the same, all right?
Mm-hmm.
Which is the same. So from here, you can see the ratio. From this case, you can see the ratio of the phi primary is over secondary is proportional to the ratio. Can you see? That's n primary. In the same way as the voltage, can you see? We're talking about, so that is how to prove that formula. Can you see? Okay, so and you can, so this formula, can we rewrite this formula? So basically, the phi primary will equal to this ratio. Can you see? NP divided by NS secondary multiply phi S. Can you see?
Yeah.
So what can we do about it? We can use Faraday's law. Can you see?
Yeah.
We can use Faraday's law. What can we do? We can use the first derivative, can you see, and plus negative sign here. So negative phi primary with respect to the time. Maybe I will use this corner. This corner is larger. Can we use this corner to finish this? So we just go to that corner. To this corner. So if I just do derivative, we got a d phi primary divided by dt will equal to coefficient np. Can you see? Divided by ns. Can you see? That is a d phi secondary dt. So we do the first derivative, all right? Second, we put the minus sign here. We put the negative minus sign in front. dt will equal to this coefficient. Can you see? np primary and ns, the secondary, equal to the negative d phi s dt. Can you follow me? Now, then we recall the Faraday's law. Can you see? We use the Faraday's law according to Faraday's induction law. Faraday's induction law. Induction law. What's that? That is the induced voltage is equal to negative. Can you see? d phi dt. All right. It's Faraday's induction law. Can you see that? And this induced voltage can also written as induced voltage. Do you understand? Induced EMF is the same as induced voltage, all right? So from this one, so we can argue that the V primary will equal to NP divided by NS, can you see? Multiply P secondary. That is why, so that result, can we highlight this result? That result is the first equation. Can you see? Can you follow me? So this result exactly is the first equation. Can you see?
Yeah.
So we have proved the two formula, right? We have two four formulas. So we got one formula and another formula here. Can you see? I hope that will help you to understand how transformer work if you look at this lesson, all right? So everything comes from what? From Faraday's law, do you agree? Of course, to derive the second formula, we have used the power formula, okay? We have assumed that the power doesn't lost. No power lost, all right? Okay, next question. Any other question? Transformer.
Oh, and I had a question about Bohr's model and light quanta.
Bohr's model and quanta. Yes. Have you Do you know the Bohr? How much do you know about the Bohr model? Perhaps that is how to we start this discussing. How much do you know about
I
the Bohr
know
model?
that he says that an atom has different sublevels that the electrons exist in, and when the electrons are in like an
Atomic
excited
model,
state, they move between the sublevels and emit energy.
Yeah, they got the orbit, right? Bohr model. And Bohr model have the orbit, right? Bohr model is built by this assumption that the electron is moving about hydrogen atom, right? Can we just consider hydrogen atom? So this red dot will represent the proton at the center, all right? And according to Bohr model, electron can only stay in certain stable or stationary orbit, right? It's called a stationary orbit. Yeah, it's not a level yet. First, we have talked about orbit. Bohr model is talking about orbital first, all right? It's just like a solar system, but the electron can only stay in one of these orbit. For example, in the ground state with the lowest energy, electron will stay here, as we learn from chemistry. Okay, also we learn this in chemistry. Do you agree? Actually, modern chemistry is built on the Bohr model. Okay.
Yeah.
So that is how the you can imagine this electron is doing the circular motion. Okay. However, Bohr model also says, so first thing, what is Bohr model? So basically the first idea is that electron orbit, okay? Electron, actually is for this Bohr model for the hydrogen atom. That is a mini article. Can we just Bohr model for hydrogen atom. Sorry, for hydrogen atom. So first thing is that the electron move in the stationary, okay? Electron stay, electron can stay in one of stationary. The stationary is called stationary orbit. Okay. In chemistry, this orbit is called a shell. Okay, so be careful. And the second, okay, should if electron also can be electron can be excited, okay, excited by absorbing a photon, all right, or energy, or even the collision, absorbing energy, absorbing a photon. You can see the photon. That is a radiation. There is a spectrum. Photon can spread itself by absorbing a photon and move to another orbit. Okay. With higher energy. So each orbital can correspond to each energy. Okay, higher energy. Okay. Now this is a Bohr model. So that is the first. This is A1. So this is A2. This is R1. So R2 is R2. Can you see? This is R3. So this Bohr model can be written as Rn equal to A1 multiply n squared, where n equal to 1, 2, 3, integer, all right? Now, another idea is that the energy level, can you summarize here? The energy level of hydrogen atom can be simply written as this formula. That is a summary. You see, n squared. Also, n is integer. You see, 1, 2, 3. And that is the electrical voltage for the unit. Okay. Now, in this case, I can use this corner here. We can draw the energy diagram. Okay. So the energy diagram is different from the orbit. All right. Energy diagram is just like letters. Can you see? So this is total energy, En. Because for the hydrogen atom, it is confined to the proton. Therefore, the energy, total energy is always negative. So this is the first energy level. Can we draw the first energy level now? So this is the first energy level. And this is second energy level. The third one, okay, and so on, you see? It gets very crowded eventually. So in terms of this quantum number, that is n equal to 1, right? N equal to 2, and n equal to 3. Okay. So electrons, the lowest energy level is called the ground state. The most stable is called the ground state. Ground state, which is correspond to the innermost orbit. Can you see? So this is also the ground state. Okay. Do you understand? Ground state is the lowest energy level. So once the photon is coming, so the photon carries certain energy coming, then electron have chance to move, to jump if this energy just match the energy interval. Can you see? I probably use a red color. So this is an important idea. So the electron can jump. Can you see? They jump from the ground state to the excited state. If they match the condition. So this condition, so this absorption condition, so that is absorption and emission. So the absorption condition, absorption and emission condition must satisfy this condition. Emission must be satisfied this condition that high photon energy must equal to the change of energy level. Can you see? So the change in the energy level. That is a summary of the Bohr model. See?
Yeah.
Yeah, we can talk about how to apply this formula next time. All right. Okay, I will stop here now. I save and stop. Okay, I'll see you Friday, right?
Yeah,
Okay.
I'll see you on Friday.
Okay, goodbye.
Okay, thank you.
You're welcome.